Good morning. All right, our next speaker is Dr. Sergio Amorata from Siprad, and he's going to be talking about how RIST on demand will enhance IPMX network and those networks that are being used for production and live monitoring of their video streams. So take it away, Sergio.
Thank you. All right, thank you, Wes. So, my name is Sergio Amorata. My company name is Siprad, and I'm also a director of the RIST Forum and an active contributor to the RIST specification. I'm going to assume that everybody already knows what RIST and IPMX is, and I will focus this presentation on how RIST on demand enhances the entire experience for monitoring and production. So here's a summary. IPMX and RIST on demand will be a central part of this discussion, but we'll place it within the context of a large project, sort of like a sample. We've been working with one of the big 3 US broadcast networks for a while now. That project uses RIST to share many feeds between New York and London, and we then distribute those feeds to locations all over both countries, US and the UK. Production personnel, engineers working from home, executives at various locations, all have to monitor and work with these feeds on a daily basis. So in this talk, we'll trace those feeds from 2110 and SDI origins all the way to the end user. So let's look at the first step in the process. We go from a 2110 or SDI encoder in London or New York to what we call the RIST sender. So, as we mentioned before, there are encoders and RIST senders at both locations, London and New York. And those streams will be distributed to multiple locations. There are actually additional locations now after this talk was prepared, and this scales up to any number of locations. On every location where this stream needs to go, we also have RIST receivers. And the users themselves, the ones that have to see the data, they can be anywhere. Not necessarily in these locations, but they can be in the headquarters office, other office, or working from home in general. So, the scope of the project, or what we did, was quite big. And at the core, we have an open source library called LibRIST in all the transmissions we did. I should mention as well that I'm the principal architect and project maintainer for LibRIST. LibRIST is a free and open source project, and we use it throughout our business as well, through radios. And the only proprietary piece we add on top of LibRIST is a fancy web GUI interface. All the working parts, all the stuff under the hood is pure, unaltered, open source binaries. So let's look at IPMX. The first step, the encoder, we'll start looking at how IPMX fits in to the equation. The encoders that we have are our own high density 2110 and SDI to H.264 hardware devices. We can do up to 21 encodes on each machine, and every one of them includes PTP synchronization software. This, of course, allows the clock to be synchronized within a few nanoseconds of the origin. In the VSF technical recommendation for IPMX, NTP can be substituted for PTP. In addition, even though JPEG-XS is the most commonly used compressed codec, we had to use H.264 in this case to achieve viable compression for transport to end users at their homes. The main takeaway, however, is that it's all about synchronizing playback across long distances and reproducing not only the timing as far as synchronization of audio and video, but also reproducing all the parts of the source stream, whether it's closed caption or other ancillary data that comes in. That's the IPMX experience. So what are our design precepts? Bearing in mind that these standards are still evolving, or even in the case of the VSF IPMX technical recommendation, some of them are not quite published yet, especially for H.264 and Wi-Fi and other things, we recommend certain precepts with an eye towards future compatibility with new standards. No one in their right mind would send a full 2110 stream uncompressed over RIST, and even with compression, whether it's LZ4, it's just too big and unreasonable to transmit that way. In any case, just about everyone is going to encode to a compressed codec for remote transmission, or most people will, the one that cannot afford 10 gigabit dedicated connections. You then encapsulate this compressed format, whether it's JPEG XS or any other one, and you push it out 2110 or perhaps MPEG-TS in our case for RIST transport over long distances. So JPEG XS would give you the lowest latency. H.264, well used, is very acceptable for under 1 second glass-to-glass in all the scenarios we had to deal with. And in the case of our deployment, we needed to achieve, the streams needed to reach the homes, which the bandwidth was a big issue. Just a minute. In any case, our goal is to allow the encoding of everything, be able to grab the source, video, audio, multiple tracks, VAC data, whatever is in the 2110 stream, and make it available everywhere else. And that is, what we think is the IPMX experience needs to be high. That's the IPMX experience. Be able to preserve all the data and transmit reliably to all the different places. So what's our approach? We want to be the live streaming king, right? So the key of live streaming is flexibility. We have a RIST receiver inside our media servers. We use the encoders to create all the video audio codecs ahead of time that are needed for playback anywhere. That way, we don't add additional latency when we need to modify the formats later on. We want to maintain all ancillary data, but strips the nulls for efficiency since they're not required for the playback devices. And we want to include a full-blown DRM solution to allow both web browser playback and STB access to the original unaltered MPEG-TS that was created on the encoders with all the streams. And lastly, we want to allow the users to be anywhere. And this was, of course, a consequence of the pandemic. That's when we started this entire project. So let's double back to the encoders and provide a little bit more detail that what we do in our encoders. All right. So one of the things we feel keenly about is that you have to decide what's more suitable for a VM or a cloud. Everybody says, "Oh, put it on a VM, put it on the cloud," versus what's suitable for big hardware or small hardware in general. For 2110 or SDI encoders, you need powerful hardware. Everybody knows that these streams can be big and demanding. In the case of our workflows, we had streams that were 1.5 gigabits per second or 3 gigabits per second for 1080i and 1080p. Whether that data was coming from SDI 2110 is irrelevant. It's still a lot of data to process. So the servers that we use were more adequate in bare metal. We used Mellanox or Intel network cards with drivers that let us bypass the network stack because the OS can be a bottleneck. We're using Linux in this case. For SDI, we use standard decklink cards, and we were able to achieve a really high density of 20 to 21 SDI or 2110 streams on a single piece of hardware. And that's including multiple bit rates. Each of our encoders for each incoming stream was able to create at least 2 H.264 video tracks and 32 audio tracks. We created 16 AAC and 16 Opus tracks for each stream. And the reason being what I explained before, we needed to be able to have all the video and audio codecs available ahead of time to minimize latency on the end-to-end delivery for the different platforms, the different viewers, whether it was WebRTC or RIST or whatever the end destination happened to be. Finally, we configured all of our encoders with RIST sender in listening mode. Basically, the open source configured in such a way that allows two connections from anywhere. And this is the core of what we call RIST on demand. This is the coined term, create the encoder, put all the data on it, put a RIST sender in listening mode, and make it available. It's RIST on demand. And we'll explain a little bit more in another slide. So what's the next step in the workflow? We push the streams to a centralized or decentralized media server. So we have the encoders, we create the streams, we publish them, and we have RIST listening, waiting to send the data anywhere. Now, we publish to the media server, right? As we mentioned, the RIST senders are inside the encoders. And the encoders, basically, the way we do it, we output the MPEG-TS broadcast compliant to its own internal network within the same machine in New York and London, and they are picked up by the RIST senders, and they're made ready to receive. The RIST receivers and the media servers are typically in VMs and not in bare metal. And the media server basically will initiate a RIST receiver connection to the listening RIST sender when needed, the specific RIST sender that needs to dispatch that particular stream. So now that the media server in the workflow has received this stream with the RIST on demand, we're going to look at the actual delivery mechanisms to the end users. We use WebRTC for browsers, and we use RIST over MPEG, MPEG-TS inside RIST for the set-top boxes. So we are using, as we mentioned before, WebRTC to the viewers. We had to create a DRM compliant solution for the management of the streams. WebRTC by itself doesn't have a strong security model. It does have encryption built in, but that's about it. Once they have, we created our system, users can just log in and play the stream, any stream within their network. And the beauty of doing it this way is that you only need a web browser, and it works on every desktop, every mobile device, every architecture, with a glass-to-glass latency of less than 1 second from your encoder to your player on the web. So here I'm showing a representation, a picture of what the corporate IPTV viewer sees when they log in. There's a pretty Netflix-style carousel menu at the bottom. It's used mostly by mobile viewers where they can scroll and scroll and scroll infinitely. But in this case, in this particular use case, we had hundreds of program choices. So a hierarchical menu, which you see here at the top right, is what was used by default on desktops, where they go log in, they have access to the stream, they click on it, they get it, the media server does an on-demand retrieval, etc. Another much appreciated feature of our web interface was the ability to do custom multi-viewers. Now that you have this translation layer between RIST and WebRTC, the client can create their own custom multi-view with whatever feeds they want. And you see an example of that on the upper left. So let's talk about the scalability and a little bit of how the system works in a global basis. Okay. As it has been discussed, and as you can see in this diagram, we've discussed something that was very large scale, hundreds of streams at a time going out to multiple RIST receivers. At any point in time, there could be 80 or 100 streams crossing the Atlantic. There can be also many viewers, many clients up as well. Thousands, in fact, are using the system. The clients can view multiple streams at a time as well, as we saw with the multi-viewer, as it's built into the web interface. So the client itself requested programs for various load balancers, in our case. And behind the load balancers, we have media server farms. And those media server farms are the ones that are going to be caching the streams for the viewers within that location. So all the media server entities, we use VMs, which makes makes it very quick to duplicate and scale up. So you can shrink down this to just a handful of streams with a handful of users to thousands of streams and thousands of users with very little effort, spinning up just a few more VMs and defining all the transports between them. So let's finish up the stream's journey and discuss an alternative method on how it arrives to the end user. Originally, the project involved only the web browser as a player, and they asked us to create a set-top box that could receive RIST instead of WebRTC, because WebRTC had a lot of limitations on the extra metadata that we can put on it. The WebRTC, if we stick to just the pure standard, is audio and video, and that's it. You cannot send anything else. So for some of the top executives, they say, we want a device that can receive all the metadata, can see a copy of the MPEG-TS with the closed caption, with everything. And that's why we went ahead and created our own set-top box dedicated to this with RIST as the protocol instead of WebRTC. So with the view that the least hardware is sometimes the most cost-effective, we created our own set-top box based on a simple Raspberry Pi. And this is for personnel typically at headquarters and other key locations that needed to have a fixed monitoring system connected to a monitor, and they wanted to use RIST. We ported our proprietary Linux OS to the Pi, and we wrote a custom interface for it that was simple to use, gave it a remote control. Which brings us then to security and authorization. For the WebRTC, we talked about how we created a DRM compliant solution, and we went through a full security audit to do it. Well, on the RIST, it was even easier because we didn't need to reinvent the wheel. RIST already has AES encryption, and it has SRP EAP256 authorization built in. So it's already as secure as it can get, as secure as it can be. So the scene transmission is highly secure, and then we added on top of that, necessary for this, the ability to have individual and group access control lists within the media interface. Now you assign a user that you saw on the other interface to an STB, and all the security is inherited to that set-top box. Now everything that the user can see, the set-top box can see. The point to make here is that the more security choices you have, the better, especially for a deployment this big. The user interface on the set-top box was designed to be as simple as possible. There's only one layer deep of menus, no need to go and dig for the place where you want to see stuff. At the same time, we added advanced search and filtering capabilities because we got 800 channels to browse through, so we had to add and make it simple to use as well. So, I don't know if you can see it. This shows the user interface, what it looks like. And on top, there's just a graph of the stream on demand and the RIST on demand and how the bandwidth goes to 0. It was a demo we were doing. But this is an absolutely standard RIST on a custom Linux OS running VLC, pretty much. We put some fancy scripting and binaries, and we created, the entire solution. Hold on. I think I pressed the wrong button. Okay. So just to summarize again, sorry. The RIST sender is always listening. The RIST receiver is on the media servers, and it does on-demand pooling. And the viewers can be WebRTC or set-top boxes. Whenever there are no more viewers, the RIST connection is closed, so you're able to have hundreds of channels available or encoders, thousands of users, and manage the entire thing with 8 small virtual machines. In the case of this deployment, they had 8 small VMs managing 5,000 viewers and 800 channels. And in conclusion, hold on, last slide. So we have shown how RIST, standard RIST, can be used to distribute large numbers of streams efficiently using RIST on demand, which is just a coin term, but it's just RIST configured in a certain way. We've shown how you can have a rich IPMX experience by having the ability to preserve the MPEG-TS across your workflow. We did that by modifying our media servers and creating solutions that not only can display WebRTC, but also transfer the raw MPEG-TS over a RIST tunnel all the way from the encoder to the set-top box or to the final destination. And we've seen how clever and efficient design of transfer solution, can make a road or give you a roadmap on how to implement a system like this on your own. Thank you.